Welcome back. In this lecture video, we'll be looking at sample size calculations for study planning when we're using ratio estimation. So we'll first look at sample size for estimating the proportionality constant K with a specified margin of error. The approximate sample size to use in order to estimate the proportionality constant K with a given margin of error of no more than E is given by the following expression. So let's take a few moments to look at this. We have the sample size, lowercase n, being given by this expression on the right-hand side of the equality. The numerator is the product of the population size, cap n, and the population variance, sigma squared. The denominator has the population size, cap n, times the square of the population mean of the x's, mu sub x, times the square of the desired margin of error. That product being divided by 4, and then we add to that the population variance, sigma squared. Now let me just remind you that in ratio estimation, what we are doing is trying to estimate the mean of the population mean of the y values, mu sub y, using the value of the population mean of the x's, mu sub x, and the proportionality relationship, which has to be estimated, obviously. So in that kind of a context, it's assumed that we know mu sub x. There are some situations where we don't know mu sub x and we would have to estimate it, but in many situations where ratio estimation would in fact be used, mu sub x will be known. So that is why we include that in this formula. Now the population variance may or may not be known. If it's not, then we would obviously have to approximate it using one of the techniques that we've looked at in previous situations. So this is the formula to obtain a sample size that would give us a margin of error of no more than E for the estimate of the proportionality constant K. So let's look at an example of this. A manufacturing company wishes to estimate the ratio of change from the last year to this year in the number of man-hours lost due to sickness. A preliminary study of 10 employee records is made, and the results are given on the next slide. The company records show that the total number of man-hours lost because of sickness from the previous year was tau sub x equal to 16,300 hours. Use the data to determine the sample size required to estimate K, the ratio of change for the company, that proportionality constant, with a margin of error of E equal to 0.01. The company has 1,000 employees. All right, so here are the data. Y is the current year measurement for values in the sample, and X is the previous year value for the observations in the sample. Now again, corresponding X and Y values are paired. So the 13 and the 12 go together, the 25 and the 24 go together, and so forth. Okay, so the desired margin of error is again 0.01. The population size, the size of the company, is 1,000. The size of the sample is 10. The total number of man-hours lost last year was 16,300. Calculating the summary statistics, we have here the sum of the x's is 178. The sum of the squared x's is 4,066. The sum of the y values is 187. The sum of the y squared values, or in other words, the uncorrected sum of squares of the y values, is 4463. And then the sum of the products of the x's and the y's is 4,245. So with those values, in particular, with the sum of the y's and the sum of the x's, we can calculate the point estimate for the proportionality constant, the point estimate being denoted by k hat. That's equal to the ratio of the sum of the y's to the sum of the x's in the sample, and so we get 1.0506. Now we don't know the population variance in this situation, and so we will have to estimate it using the data in the sample. And so to do that, we'll first need to calculate this sum of squared deviations between the observed y values and the predicted values given by k hat times x sub I. And we'll do that using the expansion formula. And so when we do that, we get a value of 31.294 rounded to 3 decimal places. From that, we get the estimated value of the population variance being 3.477. All right, so this is how we would calculate that. We have been given the population total for the x's, the total number of hours lost last year, and we have the population size. And so from that, from those two values, we can calculate the population mean of the x's, the average amount of time lost per employee due to sickness, and that was 16.3 hours. And so we have the values that we can plug into the sample size formula. And again, note that we don't have the true value, we don't know the true value, the actual value of the population variance, and so we're having to estimate it, and that estimate is sigma hat squared, equal to 3.477. And so once we do that, we plug those values in, and we get a sample size value of 343.6, and since we can't have fractional sample sizes, we'll use the next larger integer, which is 344. So if they select a simple random sample of size 344 from the population of 1,000 employees, employee records, then they should be able to estimate that ratio, the proportionality constant, with a margin of error of no more than 0.01. Now obviously, if they wanted the exact value of k, they could pull the records for all 1,000 employees in the company, but that would take some time, certainly more time than it would take to randomly sample 344 of the records. And so if it's really not worth the time to do all of that, they can get a very good estimate of k. Again, they'll be able to estimate k to within a margin of error of no more than 0.01 by looking at just a little over a third of the records for the whole company. All right, now let's look at determining the sample size for ratio estimation of the actual population mean of the y's with a specified margin of error. And so the approximate sample size to use in order to estimate the population mean mu sub y via ratio estimation with a margin of error of no more than e is given by the formula little n equal to cap n times the population variance divided by cap n times the square of the desired margin of error divided by 4 plus the population variance. All right, so let's look at an example. This is example 5, sample size for ratio estimation of mu sub I with a specified margin of error. A forester wishes to estimate the average number of trees, mu sub y, per acre on a 1,000 acre plantation. She plans to sample n 1 acre plots and count the number of trees y on each plot. She also has aerial photographs of the plantation from which she can estimate the number of trees, which is the predictor variable x, on each plot for the entire plantation. Therefore, she knows the value of mu sub x. Therefore, to use a ratio estimator of mu sub y seems appropriate. Determine the sample size needed to estimate mu sub y with a margin of error equal to e equal to 1.0. Now, a preliminary study was conducted in order to estimate or obtain an estimate of sigma squared. The data are on the next slide. So again, this is a situation where we don't know the true value of the population variance, and so we can either approximate it, or if we have preliminary data, a pilot study or something like that, we can use that to get an estimate of sigma squared. All right, and so here are the data from the preliminary study. Corresponding x and y values are paired. The y values are the actual number of trees in a given plot. X is the aerial estimate. All right, and we can see here that the values are not exactly equal. If they were, it would be an extremely good way to determine the number of trees, but they're close, and so it looks like they are very highly correlated. And so it looks like this would be a very effective way of estimating the number of trees using the aerial estimates. All right, so here are the calculations. We want a margin of error of no more than 1 unit. The population size is 1,000. The preliminary sample size was 10. All right, the summary statistics for the x's and the y's are as follows. The sum of the x's is 208. The sum of the squared x's is 4,872. The sum of the y values is 221. The sum of the squared y values is 5,469. And finally, the sum of the products of the x's and the y's is 5,144. Now, with those summary statistics, we can calculate a point estimate for the proportionality constant, the ratio value, k hat, and that turns out to be 1.0625. Next, we need to estimate the population variance, sigma squared, and to do that, we'll need to calculate this sum of squared deviations between the observed y values and the predicted y values. And so we'll use the expansion formula as before, and when we plug those the appropriate values in, we get a value of 38.03125. Okay, and then the estimate of the population variance is equal to 1 over n minus 1 times that quantity. All right, remember that n is 10, n prime is 10, and so we have n minus 1 being equal to 9. And so our estimate of the population variance is 4.2257. And so plugging that estimate for sigma squared in to the sample size formula, we get a sample size of 16.62. And so we would use a sample size of 17. And so doing that, that should allow the forester to estimate the average number of trees with a margin of error of no more than 1 unit. So again, going back up to the original question, a forester wishes to estimate the average number of trees denoted by mu sub y per acre on a 1,000 acre plantation. She plans to sample a number of 1 acre plots. The number of 1 acre plots she wants to sample is n, and count the number of trees on each plot. And so anyway, she wants to be able to do all this using a ratio estimator and determine the sample size needed to estimate mu sub y with a margin of error equal to 1.0. And so based on our calculations, it looks like a sample size of 17 would certainly be adequate to be able to come up with a ratio estimator of mu sub y with a margin of error of no more than 1 unit. All right, and then now let's look at sample size. The sample size for ratio estimation of tau sub y, the total, the population total of the y variable with a specified margin of error. The sample size to use in order to estimate tau sub y via ratio estimation with a margin of error of no more than E is given by the following formula. So the sample size is equal to cap n times the population variance divided by the square of the desired margin of error over 4n plus the population variance. And again, we may or may not know sigma squared. If we don't, we would have to either approximate it using one of the techniques that we've used in the past or estimate it from a preliminary data set. And so let's look at an example. This is example 6, sample size for ratio estimation of a population total tau sub y with a specified margin of error. An auditor wishes to compare the actual dollar value of an inventory of a hospital, tau sub y, with the recorded inventory, tau sub x. The recorded inventory, tau sub x, can be summarized from computer-stored hospital records. The actual inventory, tau sub y, could be determined by examining and counting all hospital supplies, but this process would be very time-consuming and costly. Hence, the auditor plans to estimate tau sub y from a sample of n different items randomly selected from the hospital supplies. Records in the computer list of n equal to 2,100 different item types and number of each particular item in the inventory of the hospital. With these data, a total value for each item, x, can be obtained by multiplying the total number of each recorded item by the unit value per item. Now the total dollar value of the inventory obtained from the computer is given by tau sub x, the sum of the dollar values for the 2100 items. In this particular situation, tau sub x was found to be $950,000. Determine the sample size, the number of items needed to estimate tau sub y with a margin of error of no more than $500. All right, so here are the data. Again, corresponding x and y values are paired. The y variable corresponds to the actual dollar value of the inventory. X is the dollar value of the inventory from the computer. All right, and so we want to use these data to come up with the sample size that will allow us to estimate tau sub y to within a margin of error of no more than $500. Okay, so again, the desired margin of error, cap E, is 500. The population size is 2100. The sample size is 15 for the preliminary sample size. The summary statistics for the sample are as follows. The sum of the x's is 242. The sum of the squared x values is 4,706.54. The sum of the y values, $237.50. The sum of the squared y values, 4,522.19. And then again, the units on that would be dollars squared. The sum of the x's times the y's, 4,560.27. Point estimate for the proportionality constant k is given by k hat, which turns out to be 0.9814. We need to calculate the sum of the squared deviations between the observed values of y and the predicted values of y. All right, and using the expansion formula, we get 104.3776. The estimate of the population variance is therefore 7.456, and so we'll plug sigma hat squared in for sigma squared, all right, because we don't have sigma squared, so we have to use that point estimate. And so when we do, we get a sample size of 420.68. And again, we'll take the next larger integer of 421. All right, and so using that sample size, selecting a simple random sample of 421 from the population of 2100 items, then that should allow us to estimate tau sub y to within a margin of error of no more than $500. So this wraps up our look at ratio estimation. In the next lecture video, we'll look at a similar technique called regression estimation.